Давайте подождем еще 5 минут.
А вот можно вопрос сейчас задать, да?
Да, конечно.
Вот мы когда в прошлом занятии получили уравнение дисперсии, у нас как бы вот было оно вида вот омега квадрат на c квадрат равно получается kx квадрат, деленное на некое усредненное эпсилон, и плюс k тильда квадрату, деленное на другое усредненное эпсилон. Эти эпсилон-то по сути же как связаны как раз-таки с праздным показателем преломления в unaxial crystals, то есть когда вот получается перпендикулярно вот оси и параллельно этой оси, да?
Да, конечно, это то же самое.
Мгм.
So I guess we can start today's lecture. Hello, everyone, one more time. Our today's lecture will be devoted to S-matrix theory. Well, usually it is a very powerful tool when you consider some scattering problem. For example, you have some maybe layered systems, permittivity from one side epsilon1, from other side epsilon2. You have some incoming field, reflected field, and transmitted field through this structure. So as previously, as we considered for transfer matrices, we have some linear system of equation, and we can easily find reflected and transmitted fields when you know the structure of this system. Let's now consider such situation. For example, you have some system, arbitrary for now. We don't know it for now. You again have incoming field, for example, reflected field, some transmitted, and basically we also have here, we may have here also incident field from this side. Let's say that this is the first region, this is the second region. For now, we don't know the structure of our system. We can write it like this. For example, E in first region, outgoing. So outgoing field in this region. Here, and first region also here. Two. And outgoing. So basically we can write such system. Outgoing fields are equal to some matrix, which is called S matrix, and incoming fields. So basically, this is idea of S matrix theory. It relates outgoing fields and incoming fields to our system, and this S matrix is basically 2 by 2 matrix, and tell us about the response of our system on some incoming fields. And that's actually the main idea of this theory. But we can consider some properties of its matrix, of S matrix. First of all, as always, let's calculate the Poynting vector in first region here and in the second region. So S Poynting vector. Sorry. Why Poynting vector is so important? Well, because it tells us about the transmitted power. So we have some incoming power, and we want to know how much of it transmitted through our system. Then let's try to calculate it. For example, for first region, we can say that let's call it like this. It will be incoming field minus is outgoing. Let's write the electric field. E, as previously we have some E plus, E KZ, E I K X X. Sorry, I didn't write it. And now we don't interested in Y component. And also we have minus E minus I K Z Z and E minus I K X X. Well, as you remember, to find Poisson vector, we also need to know the magnetic field. How can we write the magnetic field? Well, it's quite simple. I think you remember it. It is C over omega mu and vector product K. Let's also introduce the vector K plus K minus, which is Kx 0 and plus minus Kz, just for simplicity. So let's substitute electric field into magnetic field. We have C over omega mu A plus E I kz z E I kx, and second part minus minus I kz z E minus I kx x. So the Poisson vector, we can write it like that as z C over 8 pi real part of E vector product H conjugated. And also, because we are interested only in z direction, we should multiply it by Ez. Also, let's introduce and rewrite these exponents like Ei k z z E I k x x as I k plus r. The same with minus k z z E x is equal E. So what do we have? We have C Ez over 8 pi real part let's substitute it. Yes, plus E k plus r minus E minus r. And magnetic field. For magnetic fields, we have E plus conjugated k plus r also plus k minus multiplied vector multiplication minus conjugated and also exponent here e k minus r. And yes, and also c over omega mu. What's next? C squared over 8 pi omega mu, also ez, real part. Yes, let's rewrite it. E plus vector product of E plus times E plus conjugated. Second term is identical but with minuses. K minus E minus conjugated. We also have another two terms. E minus times K minus E minus conjugated. Sorry, not like this. What do we have next? Plus times K minus E minus conjugated. Also exponent. I will write it like ik plus minus ik minus r. And the last term, finally, E minus times K plus E plus conjugated. And also exponent K minus minus K plus R. Let's now consider each part separately. For example, this one, first part, second part, third part, and fourth. Look, for first part, we have K plus multiplied by square modulus A plus squared. But You just simply use the BAC minus CAB, and we also know that K scalar product E is equal to 0 from Maxwell's equation, since we have divergence of E equal to 0. That's why we just have this relation. For second term, obviously it's the same, just K minus E minus squared. For third part, what do we have here? Let's write. We have K minus E plus times E minus conjugated E to I K Z Z, also minus E minus conjugated times K minus E plus. It's also the same exponent to I K Z Z. And for fourth part, almost the same. E minus E plus conjugated to minus I K Z Z minus I plus K plus E minus.
Excuse me. Why we have minuses in third and fourth equation expressions? We don't have minuses in our exponents, so shouldn't be plus there.
Well, you mean in exponents?
Yes, in the upper expressions.
Here.
Yes.
Well, let's see. What do we have here? No, we should have minuses. Well, yes, because you will just expand it. You will expand this this part. Yes, you will expand this part in the same manner, like BAC minus CAB. And you actually will obtain minuses here.
Okay, I understand. Thank you.
Okay, that's clear. And also here, minus 2 I K Z Z. So we obtained answer for the first and second part. We also should somehow simplify third and fourth part. We also see that, let's consider these parts separately. and these parts separately. These parts, after we multiply it by unit vector ez, by this one, what we will obtain? We will obtain here it will be minus kz, here it will be just kz. And we also have, you see, we'll have some here, so the third plus fourth part, we can rewrite it like kz e minus times e plus conjugated multiplied by exponent minus 2I kz z, and minus almost the same z z. So it's the sum of this dashed parts. What do we see here? We see that it is imaginary. So when you will subtract it, you will obtain imaginary part. Is it clear why this expression is imaginary? So it's just the complex number minus conjugated complex number, and you will obtain two.
Excuse me, it's like a sinus because we have the one exponent minus another exponent. It's sinus multiplied by e, yes?
Yes, but the main reason that it is imaginary, just purely imaginary number or vector. So as far as we know, for Poynting vector, we should only calculate the real part. Then for Poynting vector, this one will be 0. We will not be interested in these parts. So let's consider the other ones. These wavy lines. How can we rewrite this multiplication? So k minus e plus. It is obviously kx e plus x minus kz z plus. We also can just say we plus kz ez plus and subtract it kz ez plus. What is it? It is 0. So the final answer for it is minus 2kz ez plus. Obviously, for k plus e minus, we will have the same expression, but with plus. Kz e minus. So for third and fourth parts of the equation, we finally can write this ez minus complex conjugated times 2kz plus z on exponent to ikz z and minus z plus complex conjugated 2kz z minus 2ikz. Well, again, we see that it is also imaginary number, because again, we have some complex number and we subtract its complex conjugated. And we will just obtain two imaginary parts of this number. Again, for Poynting vector, we are interested only in real parts. So for now, for us, it is also 0. And the final answer for Poynting vector, it is quite simple. That's e squared kz 8 pi omega mu, and what we obtained for the first, we just left with first and the second part. E plus squared minus e minus squared. So this is quite simple expression for Poynting vector in such system. But usually in this theory, people introduce these vectors of incoming and outgoing fields. C kz omega mu plus vector z and b1 outgoing field z by omega mu e minus I kz. Yes, so it is relations for incoming and outgoing fields in the first region. So from this we can rewrite that Poynting vector have very simple expression: 1 squared minus b1 squared. Okay. So now, for simplicity, let's consider only TE waves. As you remember, we have only a y component of electric field in such situation. So let's rewrite it. Ey for the first region. Also, let's call it alpha minus 1. We will have alpha A1 plus B1 E I K X. And magnetic field, we are interested. We have two independent components of magnetic field, as you remember, and now we are interested only in x component. C over mu alpha, and here we have the from this equation. We should multiply wave vector on electric field. And we obviously will obtain minus kz A1 minus B1 EI KX X. Kz just is a consequence of the vector multiplication. You have EX, so kz here, and EY. You will need to know EY, and when you will multiply it, you will just obtain minus kz. For the second region, we just need to change kz to minus kz. So let's write it. E2y alpha tilde. Alpha tilde, just because we might have different permittivity in the second region. So basically, it might be different. So A2 plus B2 EX and magnetic field second region E over omega mu. Actually, here also mu1 and mu2 because it can be different. But here kz tilde because kz contains the epsilon. E2 minus B2 kx. So these are fields, electric and magnetic fields for the first and for the second region. So by definition, we can relate these fields as our S matrix A1 and A2. So it's just by definition of S matrix. Well, again, it relates incoming fields and outgoing fields in our arbitrary system. But now let's consider some properties.
Excuse me, shouldn't we have different kx in the second region?
Yes, if we have another permittivity, it should be kx tilde.
Well, okay. Strictly speaking, yes. Okay, thank you. So properties. Let's say that, for example, in our system, in this so-called box here, there is no loss of energy. So the energy is conserved in such system. Then we can write that as Poynting vector in the first region is equal to Poynting vector in the second region, because energy is conserved. Or in other words, as we know, this one is A1 squared minus B1 squared, and this one is B2 squared minus A2 squared. So why B minus A in the second region? I guess it's clear. Well, it is obviously because we have a different direction of kz. So in other words, we can write it squared plus A2 squared equal to B1 squared plus B2 squared. Or in other words, it is related like this. Then we can say that a Hermitian conjugated, it is just as Hermitian conjugated as A. And this leads to property that our S matrix is unitary matrix if the energy in our system is conserved. So this is first property. The second property related to time symmetry. So first of all, let's consider the solution of the wave equation that we already considered in waveguide theory. So electric field that of electric field of time and space is just the d omega 2 pi over force and our plane waves. Sorry. Okay. And omega k. We know that actually this electric field is just it is a physical field. So what we observe in real life. So it is real, because in real world we see only real numbers and real things. So let's just complex conjugate it. let's just complex conjugate this. Omega to pi. Now we have e I omega t minus I k r e omega k. And now, as previously we did it, let's change omega to minus omega and k to minus k. And we actually will obtain the, also I forgot here, the complex conjugated field. We obtain 3 omega 4 in the same exponent minus I omega t plus I conjugated minus omega minus k. So we have the same exponent, same plane waves well, here. So they generate a complete set. It is a basis, and so on. You already know it. We considered it a lot of times. So this leads us to, I'm sorry, it happens sometimes. So do you see the screen? Is it okay?
Yes, it's okay.
Okay, thank you. So now obtain such relation. We already did it in the waveguide theory, but now let's do the same thing with time. So e minus t r. So I will just, I don't want to write it. I will just call it a for simplicity. What we'll have? We'll have I omega t plus I k r. Omega k. We can again change omega to minus omega, k to minus k. What we will see? Again, write a minus I omega t minus I k r e minus omega minus k. On the other hand, we know already that it is the same as here, almost the same. I will rewrite it a e minus I omega t minus I k r. We can substitute this relation that we already obtained. Okay. So if we have a plane wave solution, some now I will call it b already, e minus I omega t plus I k r. So some plane wave traveling in our system. When we perform the time reverse to minus t, we will just obtain the conjugated part of the amplitude, and we have to change the sign of the k, ikr. Or in the S matrix formalism, you see we have in first case we have simple incoming fields, outgoing fields in this part. Also here the B2 and A1. This is the main scenario. When we perform the time reversal symmetry, what we have to do? We have to conjugate the amplitudes and change the direction of k. So in this case, it will look like this. So complex conjugated, B complex conjugated, A2 complex conjugated, and B2 complex conjugated. So the incoming fields became outgoing fields and vice versa. And in this case, we write A2 conjugated, our S matrix, B1 conjugated, B2 conjugated. If we will conjugate this expression, what we will obtain? We will obtain B1, B2 equal to inverse S matrix, A1, A2. And this leads us to second property of S matrix. Also from the first property, from this, what we can write? We can write that S plus equal to S inverse. So altogether, S conjugated equal to S inverse and S Hermitian conjugated also equal to S inverse. What we can say, which result we will obtain? Obviously that transpose matrix equal to its initial matrix. Is it clear why it's so?
Yes.
Okay. Just in case, I will write that S plus, it is just S transposed and conjugated. It is Hermitian conjugation. So actually, this results in reciprocity. So it says that if it's so if our transpose matrix equal to S, we can say that our system is reciprocal. We can actually demonstrate it also through Maxwell's equations. And we can say it is called Lorentz reciprocity. Yeah. Maybe some of you already know about reciprocity theorem, but let's show it from the Maxwell's equations. So, for example, we have two independent solutions of Maxwell's equation. We have two sources, for example. Let's write the curl equations. Due to the first source, let's say source some source in our system. For the first source, we have 1 I omega H1 for magnetic field. 1 for pi C J1 minus I omega epsilon C E1. This is the first source, but we also have the second source. As we said, we have two independent solutions. For the second, we can write almost the same equations. H2 I over C minus I omega C E2. So let's now just multiply this equation H2, this on E1, and this for H1, and this for H2 or E2. Yes. No, here. E1, okay, E2. Yes, now it's correct. And let's subtract. Let's consider this equation, for example, and this one. And let's subtract second equation from first. What we will obtain? Here we have H2 curl E1. From the second equation, we have E1 curl H2. Here, I omega mu over C H1 H2 product minus 4 pi over c j2 e1 plus epsilon c e2 e1. What we see here. It is just the divergence of E1 vector multiplication H2. So for the second part of equation, we can rewrite the same thing. I will write it. Omega mu I call it like first, second, omega over c h1 h2 minus 4 pi over c j1 2, almost the same, but indices different. E1 2 and is equals to divergence E2 H1, just like here. What we can do, we can subtract the second equation from the first, for example. So we'll have the divergence E1 H2 minus divergence E2 H1 from the left hand side, and from the right hand side we will just have the currents. I will see J1 E2 minus J2 1.
I think you forgot. No, sorry.
Okay. So it is quite the answer, but now we want to integrate it over volume, both parts of these equations over volume, and we will have two cases. So for example, the first case integrate over volume. We have the first source. We have, for example, second source. How to choose the volume? How to calculate it? For example, we can choose some arbitrary volume here, which doesn't contain the sources. And due to this fact, obviously the second part of the equation equal to 0. because our volume doesn't contain sources. It is 0 inside the integral. So what we're left with, integral volume dv, and it equal to 0. As a consequence, this leads to dv what it leads to is use the Gauss theorem ds also dv and h2 e1 ds. Here is dv is just the boundary of our arbitrary volume. So this is the reciprocity theorem in this case when our volume doesn't contain sources. This actually results to this relation that we obtained for S matrices, but it has to be proved actually, but maybe I will prove it later. It was the first case. We also have the second case when we can transfer our arbitrary volume to infinity. What we will have in this case? So we move far away from our sources. So we calculate far field. So in the far field, we just have our plane waves, and this results in so in this case, our divergence from the left-hand side of the equation is equal to 0. Well, it is simply because in this case, magnetic field is just proportional to normal product, normal vector E. So the divergence will be 0 in this case. And finally, we have this expression E2 EV J2 E1 dV. So this is reciprocity theorem. Maybe some of you already encountered the reciprocity in other courses. And maybe you know how it is related to the Green's functions. Let me say a few words about the Green's function. So let's look how it is related to the properties of Green's function. We just Green's function. So we just take the curl of E, obtain the wave equation. What we will have in the end? We will have something like this. Squared C squared plus delta E equal to minus I omega mu over C squared and our current J. So we have a sources. That's why we have the non-zeros right-hand side of this equation. And how we can write the solution of this equation? Obviously, it is possible to do through Green's function. So we can write it like omega squared epsilon mu C squared plus delta our Green function R prime. It is freezes again. Let me reopen it. So it is just a delta function. R minus R prime. It's just a well-known solution of standard equation with sources through the Green's function. So what our field look like? It's just integral over Green's function R minus R prime and this part I omega mu C squared and also 4 pi. This is our source. J1 R prime, the position of source. So we can substitute this as the solution to the reciprocity theorem. What we will obtain? J1 R also dr prime, our Green's function minus R prime and J2. Also here we should write some indices for Green's function and sources. So it will be alpha and here beta. Well, why? Because here it's just a vector. Also this one also a vector. So our Green's function is a tensor. We have two sources and Green's function tensor. It is the left-hand side. Let's write right-hand side. CR I'll write it like one integral dr prime g2 alpha this function r prime and, g2 alpha, yes, and j1 beta of So what we see here, let's a little bit rewrite it. dr prime our Green's function, I will put it like alpha beta. I will not write r and r prime. j1 alpha j2 beta equal to dr prime, also Green function alpha beta, and j2 alpha j1 beta. And as a result, we can write that j alpha beta over some x position equal to j beta alpha, just as with our S matrices. Also, it is quite easy to find S matrices if you know the Green's function and the structure of your system. So this is small thing about the Green's function. Here's also X. So we have, let's return to S matrices. We have our three properties. S plus S equal to 1. Second, minus inverse matrix conjugated. And third, transpose S matrix to equal to the same S matrix. This is our three properties. And what is the physical result of these properties? Let's just consider every of them independently. So but first, I think let's have a 10 minutes break, and then we will continue. So continue in 10 minutes. So let's continue. Yes. So our properties of S matrices. We also can write the S matrix as S11, S12, S21. Just explicitly write the components of this matrix. So let's consider the first property. We can multiply it. So 1 conjugated, S12 conjugated, S21 conjugated, second matrix S2, S, and it equal to unitary matrix. So what can we write from it? We can write S11 squared plus S21 equal to 1. The second equation squared equal to 1. Just from matrix multiplication. And also we have the third one, S11 conjugated S12 plus S21 conjugated S2 equal to 0. This is our equation from this property. What do we know? We know that after we transpose S matrix, nothing happens. So we can say that S12 in this case equal to S21. Perfect. Then from this first and the second equation, what do we have? We have just S11 squared equal to S22 squared. And if we will rewrite it, 1 equal to S22, it is just square root of minus this component, 1 component of S matrix. And what now? Now we can rewrite the whole S matrix. So what do we have here? S11 1 minus S11 squared. Here's the same because they are equal. S11 squared. And here, actually, it may be different. So I will just write explicitly, rewrite the amplitudes and the phases of these components of these fields. So here I will just write E phi1, here I phi2. Here's also I phi2 because these components are equal. And here here's some I phi3 is the same. So in general, these phases can be different. So what do we have in general here? We have 4 independent parameters. So 3 phases and 1 matrix component, S11. Just to solve it, we also need one more relation here. So consider the second property, the inverse matrix. So I will rewrite the second property. S conjugated. This one. So here we need to find the inverse S matrix. So how to find it? I hope everyone remember the linear algebra. This is just determinant S multiplied by aggregate matrix S. So aggregate S, or in Russian, присоединенная. So let's look only on one component of the matrix, inverse matrix. So here I will write determinant S. What do we have here? We will have E I phi3 S11 and other components which I'm not interested for now. From the other hand, what do we have? We have complex conjugated minus I phi1 S11.
Excuse me, shouldn't it be exponent EF1 in the first matrix? Because you wrote F3.
No, it is aggregate matrix.
Okay.
Let me do it clear. When you have matrix A, B, C, D, the aggregate matrix will have the following form: D minus B minus C, A. So here's D component of the matrix. So here's the phi3. Now it's clear?
Yes, thank you.
So for the first component of this matrix equation, what can we write? I 3 S1 equal to determinant S multiplied by I minus 1 S 1 1. We can just do it like this. What do we have? We have E I phi 3 minus no plus phi 1 equal to determinant S. Or from the other hand, we can calculate the determinant of our matrix S here. Let's write it. E I phi 1 plus 3 S 1 1 squared minus E2 minus 1 minus S1 1 squared. It is our determinant. So what do we have next? E I phi 3 plus phi 1 here 1 minus S1 squared equal to minus E2 I phi 2 1 minus S1 1 squared. So what can we say here about phases?
We can say that all phases if phi1 plus phi3 equals to we have to got -1 into the exponent. Yes, it would be like, as I remember, minus it would be EP. Yes, it would be phi3 plus phi1 equals minus EP, just EP plus 2 phi2.
But without I, we just
Yes,
have
yes. There's P.
So phi 2 plus phi. Yes, but in general, actually, we also should write here 2 pi n. But for simplicity, let's just say that n is equal to 0 and just 2 phi 2 plus p. So we found relation of phases. We left only with 3 independent parameters now. And what we can do next? We can consider some examples. For example, firstly, let's calculate the S matrix for some empty space, so for vacuum. So you have some space here, 0, L. What do we have? We have some incoming field again, outgoing. Let me call it like E1 plus E1 1 minus. And we know that this is A1, this is B1. Here what we have, E plus in the second region, or A2 here, B2, and E, sorry, E minus in the second region. So here electric field, some component of electric field, it is actually doesn't matter for now which component, because we are in vacuum. So how fields A1 and B1 are related to each other? Obviously, they are not related at all, because we just have empty space, vacuum. But we can find the relation of B2 and A1. So they are related with phase. So the wave traveling through the distance L will obtain some phase. Or what we can write? We can write B1, B2. Zero, zero, because they are not related. I, K, Z, L, sorry, L. Here's the same exponent. KZ, L. And 1, 2. Is it clear that we have the same sign in the exponent? Well, it's obviously because KZ changed direction, and also Z changed direction, because we can write the phase like I, K, Z, Z. So in this point it is 0, and in this point it is L. So wave traveling from this direction to this direction will have here 1, because of the exponent is 0, and here it will obtain phase KZ L. So this is our S matrix for empty space. I, L. Well, we also can consider another example. What if we have some, here, right, some empty space. But what if we have some semi-transparent mirror? When we have mirror, you know that we have some reflection coefficient. So I will draw the mirror. It is thin enough, so we have reflected field. And here also we might have this situation. So we have coefficient R reflection coefficient. And we can choose the plane, this plane, let me see, at which we will observe our fields in such way that B1 will be equal to minus R A1. So in this case, we can write the S matrix. So minus R, here the transmission coefficient. But here we also have phase. As you remember, we phi3 plus phi1 to phi2 plus p. Sorry. Sorry, I forgot something here, I guess. No, here is correct.
Shouldn't.
Yeah, we also will have here phi1. So phi2 minus phi1 plus p. So in this case, we have phi1 equal to phi and phi3 equal to pi. And it leads to phi2 again. Equal to pi over 2. What it means? It means that
Why we have imaginary part in all diagonal elements before transmission coefficient, like E multiplied by square term.
yes, exactly. It means that here we have I. This is our phase for these components. So it is the case of semi-transparent mirror. Let's calculate more physical, more real thing is S matrix for Fabry-Perot resonator. So as you remember, Fabry-Perot resonator is just two mirrors with reflection coefficient 1, reflection coefficient 2, and also transmission. Just simple and well-known system. Again, we have some A1, B1, and here B2. the thickness of the resonator is D. So what do we know already? We know S matrices for each mirror because we already obtained it for semi-transparent mirror. But in order to find B1 and B2, we also need to find fields inside the resonator. So we can draw it like here we have A tilde and B tilde. So our wave entering the our wave is transmitted through the first mirror, and then it travels inside the resonator. It's just reflects from the first mirror, from the second mirror, then go back to the first mirror, and then again reflects, and so on and so forth. So to find it, we should know these fields inside the resonator. So let's try to find it. First, we start with A tilde. What do we have? I also will rewrite the S matrix mirror in such way. For simplicity. So what do we have? First of all, wave transmits. We have IT1 with amplitude A1. Then it goes through the distance of through the thickness of resonator, acquires phase I KZD. Then it reflects from the first or from the second mirror and going back and again obtain the phase IKZD. Then again it goes like minus R1 reflects from the first mirror. For simplicity, I will call this phi, EI phi minus R2 again, I phi, and also I will call this part is as A0, and here A0, and then again plus and so on. What we will have in the end? In the end, we will have some 1 plus R1, R2, E2, I, V plus R1, R2, E2, I, V squared plus so on multiplied by A0. Or we can just simply write that it equal to A0 divided by 1 minus R1, R2, E2, I, V. Okay. Then for for B1, what do we have for B1? For B1, we have minus R1, A1, because field A1 reflected from the first mirror. And then also I T1, A tilde, because field inside the resonator transmitted into the first region. And what do you have? Minus R1 plus 2 1 squared E2 I P divided by this denominator. Multiplied by A1. Let's open the brackets. Here we have
excuse me, if we had A tilde as if we have A tilde equals to something multiplied by A0, where we get A0? Maybe we can't just put A1 behind the brackets. Yes, sorry.
yes. Okay. Minus R1, 1 minus R1, R2 exponent to I phi plus R2, 1 minus R1 squared E2 I phi. And here, yes, also A1. What can we do next? We can just delete these parts. And in the end, we will have minus R1, R2, I phi, and the same denominator. 2 A1. What is it actually? Now we found the S, no, just without it, like this. We found S11 coefficient of our S matrix. What do we have next? We also have B2 here. What is B2? B2 is just the IT2 and B tilde. And again, we have to find the B tilde. Well, just let's quickly do it. IT1, A1, E I phi plus R1 R2 Y phi, the same I T1 A1 E I, and again like previously, so on and so forth. And then as the result, we can write that I T1 E I phi A1, the same denominator. Yes, and finally B2, know it from here, nothing else that T1 T2 E I phi phi A1. So finally, we can construct the whole S matrix for Fabry-Perot resonator. We have sorry guys, I just got dropped. Let me give me a minute just to fix it. Oh, I'm sorry. So I guess you hear me now. Let's see the broadcast. Mhm. Mhm. So what do we have in the end? In the end, we have quite simple relation. T1, T2, E, phi, and also T1, T2, I phi. Так, я не понимаю, почему меня дропает. So I need just a couple of minutes to finish, and we will end for now. So to find, we found this coefficient, and to find this one, you just have to solve this problem from the other side. And the only difference is that indices of reflection coefficients will be changed. You can check it if you want. So this is our S matrix for the Fabry-Perot resonator. We actually can find a lot of stuff with it. You already know the transfer matrices. Now you know the scattering matrices. You just can analyze a lot of structure with these methods. So I guess for today, we will stop here, especially because of some internet connections. If you have any questions, please ask. Do you hear me at all?
Yes.
Well, okay. So if no more questions, we will end our lecture.
Goodbye.
Thank you. Goodbye.
Thank you.
Okay, goodbye, thank you.
Да, я хотел только сказать, Ксения, вы еще здесь?
Да.
Я хотел сказать про защиту домашек на последней паре. Мы хотим вот сделать то же самое, что на мидтерме, но я помню, что последняя пара, она пересекается с защитой НИР у нас. Поэтому мы защиту НИР двигать не будем, мы подвинем пару где-нибудь на четверг, наверное, где-то так. Вообще это нормально будет? У вас там есть что-то, или какие-то пары, там, или экзамены? Там?
Ну,
Или
у
это
нас
можно просто в
где-то
расписании?
в этих датах есть мат-методы, которые тоже пока до конца не поставили,
Мгм.
как я понимаю. В связи с этим может быть какая-то такая сложность.
Ну,
М,
хорошо, вы, если что, держите в курсе меня, если у вас там что-то будет. Я сейчас предварительно попрошу Дашу передвинуть пару на четверг. То есть
Во сколько?
с 24 числа на 26. Ну, во сколько хотите.
Ну, наверное, пока что так же. У нас
Давай.
26 же, кажется, уже не учебный день, насколько я
Ну,
помню.
по-моему, там зачетная неделя начинается. Что-то
Ну
типа
вот.
того. Да, ну, давайте также там в 10 ориентировочно. Если что-то поменяется, то я
Хорошо, мы
напишу.
вам напишем. Ну и
Или
мы
вы
вам
мне.
напишем, если у нас будет мат-методы в это время.
Да, без проблем.
А какие
Все,
есть
так.
еще опции переноса? Нам, не знаю, на среду опция
На,
открыта?
на среду опция открыта. Ну, я просто так
Хорошо.
сказал.
Да, хорошо. Спасибо. Ну, сейчас напишу тоже. Мгм.
Все, тогда я вам сегодня еще пришлю домашку небольшую.
Хорошо. Спасибо.
Все,
До свидания.
спасибо. Всем пока.